Hello viewers, today we are going to start our series on continuity and differentiability, and the very first concept that we are going to talk about is of continuous functions. The concept of continuous functions is very close to the literal meaning of the word continuous. A process or an event is said to be continuous if it continues without stopping, and that is exactly what we are going to look at through graphs of functions first. Here we have graphs of two functions which seems to be very smooth, running without a break or a gap, and that is exactly what we are looking for as we discuss the concept of continuous functions. What about these two graphs here? If you have to trace them with a pencil or a pen, would you be able to do that without lifting your pencil? Surely not. What about this one? This also seems to have a little hole at x is equal to 1. Do you see that small hole at x equal to 1 marked by a small circle in black? Even if you do not have to lift your pencil too high, it still brings a break in the graph. Such functions would be discontinuous functions. Let us examine these functions a little closely to see what creates this discontinuity. Here we have a function, one of the earlier graphs. Function here is defined as when x is less than 1, f x is equal to 1. When x is greater than or equal to 1, it takes the value 2. Now, what this definition of the function do is, it gives two different heights to the function for x less than 1 and x greater than 1, and that is what causes this gap between the two graphs, and therefore results in a discontinuity. Whereas in this one, the function is x square minus x by x minus 1, clearly not defined at x is equal to 1, and so x is equal to 1 is not in the domain of the function, and therefore you have to leave a little mark, a little gap at x is equal to 1 when you draw the graph of this function, and therefore again discontinuity because the function is not defined at x is equal to 1, whereas as compared to the previous graph, from both the sides of 1, it is going towards the same height, right. What about the third one here? Again a very peculiar situation. At x is equal to 1, the graph is definitely not defined, the function is not defined, 1 does not belong to the domain. What are the other two things that you can observe as you see this graph? When x takes values less than 1, do you see the graph, pink graph on this side, plunging right towards the negative infinity, whereas on the greater side of 1, very close to 1, as x takes values very close to 1, but more than 1, the graph seems to be going up towards positive infinity, again giving rise to a break in the graph. So, what we have observed right now with these three graphs are the various reasons for which the function becomes a discontinuous function. So, how would one define a continuous function at a particular point? What you need to understand is that the function will not show such behavior if at a particular point the function takes the same height from the two sides of the point, right. And most importantly, the function must be defined at that point, and the actual value, that is the attained value of the function at that point, equals what we call as the intended height of the function. So, the function converges towards the same height and the height exists at that particular point, then there will be no reason for the graph to have a break or a gap. And that is what our concept of limits also said something. It said something about converging towards the same height, but the height need not exist, remember. So, let us put it all together and give you the definition of continuous function at a certain point. The definition says, suppose f is a real function on a subset of the real numbers, and let C be a point in the domain of f, then f is continuous at C if the limit of f(x) as x tends to c equals the value of the function at x is equal to c. Isn't that what I just described by saying that the intended height must be equal to the attained height? The function must converge to the same point, the same height from the two sides of x is equal to c, and there should be an f of c as well there. So, that is what we are going to now examine algebraically given a function. You know very well that graphs are not so easy to define and draw without a particular software. You are very restricted in terms of defining and plotting those graphs of functions which you will now examine algebraically. So, we would expect you to have a very good understanding of the algebraic method of finding or discussing the continuity of a function at a particular point. So, let us begin with our very first problem, and the question says examine the continuity of the function f at x is equal to 0, where f of x is defined as x minus mod x by x when x is not equal to 0 and takes the value 2 when x is equal to 0. Now, every time you see a function which involves modulus, absolute value function, the very first thing one must do is restate, rewrite, define it again, keeping in mind that the behavior of mod x depends on whether x is greater than 0 or x is less than 0. So, keeping that in mind, let us redefine our function, and we have the function rewritten for x greater than 0, taking the value 0 because mod x is x, simplify and you get f x is equal to 0. When x is less than 0, mod x takes the value minus of x, and therefore, it all simplifies to 2. At x is equal to 0, the function takes the value 2. So, we are interested in showing that the left hand limit is equal to, or in fact discussing whether the left hand limit is equal to or right hand limit or not. Left hand limit at x is equal to 0 is given as limit of f x as x tends to 0 from its lesser side. That is denoted by 0 with a little negative marked as superscript there. What is this going to be same as? Limit of 2, because when x is less than 0, f x is 2, and limit of 2 no matter where x is going remains 2. Similarly, the right hand limit is limit of f x as x approaches 0 from its greater side. What would that be same as? When x is greater than 0, f x is 0. So, it is limit of 0, which remains 0 as x approaches 0. And therefore, obviously, the left hand limit is not equal to right hand limit, but what about its comparison with the value of the function? Well, yes, the left hand limit does equal the value of the function, but not equal to right hand limit. That would still give rise to a discontinuity at x is equal to 0. I hope that made sense to you. Let us take another problem, slightly more complex, more of discussion to be done here. The problem asks for finding the value of an unknown a such that this function, which is defined differently for x less than 0 and greater than 0 and at x equal to 0, such that the function becomes continuous at x equal to 0. Now, this is one of the problems which I have picked up simply because it will brush up lot of techniques of limits for you. So, get ready. For x less than 0, it is a trigonometric function, right? Greater than 0, you have irrational factors. And what do we do when you see an expression like that in terms of evaluation of limits? We use rationalization. So, we are going to bring up both the methods as we go further with the solution. Very first thing, f of 0 is a, that is very clear, defined, let us put that at rest. Left hand limit is limit of f x as x approaches 0 from its lesser side. That is same as replacing f x by its definition when x is less than 0. We use the basic trigonometric identity 1 minus cos 4 x to be same as 2 sin squared 2 x, and that rewritten, redefined so that you can use the limit sign theta by theta as theta tends to 0 to be 1 becomes same as just 8. What about the right hand limit? Again, as we take x approaching 0 from its greater side, f x gets replaced by the function root x by square root of 16 plus square root of x minus 4. And as we said earlier, we use rationalization. So, if I multiply and divide by the conjugate of the denominator, I get simplification to a large extent, and you can see how nicely it just simplifies to root of 16 plus root x plus 4. And as x tends to 0, what would this be? Nothing but root 16 plus 4, which is 8. And so, the left and right hand limit both are same as 8. Value of the function was also given as a. Limit exists equals 8, and therefore, for continuity the left hand limit, right hand limit and the value of the function must be equal. Doesn't that give us the value of a as 8? So, a question which brought up lot of interesting techniques that you may have forgotten because this is what you learned in grade 11, suggests that you do need to brush up the concept of limits before you try your hands on continuity of the function. At the same time, there are a number of small but significant results which we need to be ready with. So, get down to writing them down and keep them in mind as we progress further down with this topic in our subsequent lessons. One of the results suggests that if f and g be two real functions continuous at a real number c, then their sum, difference, product and the quotient with the condition that g of c should not be 0, they all are continuous at x is equal to c. We also have an understanding and a result about the composition of two continuous functions. So, if f and g are two real valued functions such that the composition f of g is defined at c, g is continuous at c, f is continuous at g of c, then we say that f of g is continuous at c. Another very important understanding is what do we mean by continuity over the entire domain, because our earlier definition was about continuity at a particular point. We say that a real function f is said to be continuous if it is continuous at every point of the domain of f. We also have a definition for a function to be continuous over its entire domain. A function will be continuous if it is continuous at every point of its domain. This and our next list of results which tell us what are those standard functions which are always continuous is going to help you build up on the further concepts that you are going to come across in this chapter. We have results which suggest that every polynomial function is continuous, every rational function is continuous, sine and cosine functions are continuous, absolute, logarithmic and exponential functions are continuous. These are results which are not too difficult to prove, but for the time being we are not covering their proofs, but we will be using and referring to these results in our future lessons. I hope today's lesson has brought in some clarity on this abstract concept of continuous functions. We will continue with more on continuity and differentiability in our subsequent lessons. Thank you.